Let's talk about recognizing our exponential functions within tables while doing a comparison to our linear functions. So on this table, we have a mixture of linear and exponential functions. Both of them are dealing with these inputs of x values -2 to +2. So one spot that we can look at first is just where x equals 0 and the outputs from x equals 0, because these values can be seen in the function forms, both exponential and linear. When it's linear, it comes through as that y-intercept, or that value for b. So with linear, when we're referring to letters, it's y equals mx plus b. And then with our exponential function of y equals a times b to the x, which, we'll have this little overlap of b, but I'll be sure to distinguish when it's linear versus exponential. But when it's exponential, those values where x equals 0 comes through as the value for a. So you can see that 2 there and that -3 there. So when we're looking at tables, if we need to form the function, look for x equals 0 or find x equals 0, and from there you can get a piece of the puzzle. Now let's talk about seeing our slope versus our growth factor for our functions. So something I want to notice is that with x, there's this nice change of just adding 1, adding 1, adding 1, adding 1. So with that, I don't need to worry too much about what's going on with x when I'm looking for these kinds of rates of changes or factors of change. But we'll talk about down below when x has different kind of changes going on and how that affects the function. But for now, x is all good. We're just going to focus on how the outputs change. So I'm going to do is see what does it take to kind of move between these output values. So to get from 1 to 4, could add 3. Now we could also multiply by 4, like 1 times 4 would give us 4. However, when I get to the next step, to get from 4 to 7, well, multiplying by 4 wouldn't work, but adding by 3 would work. And 7 plus 3 is 10, and 10 plus 3 is 13. So what we can see is our rate of change coming through as this constant amount that we're adding on, and that gives us the slope of our function. And in fact, let's jump over to our other linear functions so that we can see how that comes through. I'm moving between these output values and how we would be subtracting 2 each time. And that's where we get our slope. It's this constant amount that, in this case, that we're subtracting each time. Now, with the exponential functions, we go and look for how they change step to step. I'm just going to ignore the fractions for a moment. Let's say I start at 2. I say, okay, to move from 2 to 6, I can either add 4 or multiply by 3. To know which one I want to use, look for how to get from 6 to 18, and we'll see we want to multiply by 3. Multiply by 3. And then we could see here with our fractions that is coming through, like 2/9 times 3 is 2/3. Get this like cancellation. Oh, let's do a little fraction review here of 2/9 times 3. You get this cancellation happening, so you'd have 3 left over in the denominator. We'll talk a little bit more about fractions down below there. And 2/3 times 3, well, those denominator and 3 would just cancel out, so we'd be left with 2. So the growth factor comes through as this number that we multiply by every single time. So with linear, it's addition or subtraction. With exponential, we're going to see multiplication. So here, the idea is 1/2 would be the amount that we're multiplying by each time. So you can see times 1/2. So that would give us -6. Times 1/2 would give us -3. Times 1/2 would be -3/2. Times 1/2 would give us that denominator of 4. So in terms of reading from tables, we can see our functions by looking for that y-intercept, and that will give us a piece, and then looking at how the outputs change, and is it coming through as addition and subtraction, or is it multiplication? And that'll tell us whether it's exponential or linear. So let's do this in kind of an opposite way of being given the table and see if we can find our function. So again, if it's linear, we want this y equals mx plus b. If it's exponential, we want y equals a times b to the power of x. And actually, I'm going to use function notation. I know it doesn't really make a difference, but f of x and f of x. All right, so this first function here. What I'm going to do first is check out the x values and see how they're changing. So I can see is here they're just bumping up by 1, bump up by 1, plus 1. So that I don't need to worry too much about x with this. So I'm going to look at y and how y is changing. So to get from -9 to -5, I typically start with linear, just because it's kind of easier to think about addition, subtraction of things. So to get from -9 to -5, I would need to add 4. And I could see, well, to get from -5 to -1, add 4. And then it just has to hold true across the entire table, which it does. So what we get from this is, since we're adding, that tells me that this is linear. And with that, we have our slope of +4. And we have our y-intercept because they were nice enough to give us x equals 0 with an output of -1. So for this table, we're getting f of x equals, so m will be +4 times x, and then a y-intercept of -1. All right, let's go over here to the right. Now, mixed numbers are helpful when writing sentences. I think in terms of word problems, they're great for displaying a number, and they're easier for us to interpret compared to improper fractions. However, when you're doing math, improper fractions are much easier to use. So what I'm going to do is change these to improper fractions. So this will be some nice review of that. How I think of it is you take your denominator times the whole number piece, so 3 times 1, and then add it with your numerator. So I'm thinking of as 3 times 1 is 3, plus 1 is 4. So 1/3 is the same thing as 4/3. 3 times 2 is 6, plus 2 is 8. And 5 times 3 is 15, plus 1 is 16. And 3 times 10 is 30, plus 2 is 32. All right, so now that I have my improper fractions, I'm going to check out what x is doing. That looks good. It's just bumping up by 1 each time, which is perfect, so nothing extra to think about there. So now I'm going to focus on what's happening to the outputs. Now what I can see is the denominator's not changing at all. And with that, I can kind of ignore the denominator then. Now if that's staying constant, nothing's being added to or multiplying the denominator. So it looks. So for there, I'm just going to focus on the numerator. So 4 to 8, 8 to 16, 16 to 32. What I can see is that we are doubling values. So we are multiplying by 2, multiplying by 2, multiplying by 2. So what we have here is our growth factor. So, well, first of all, this tells me that this is exponential because we're multiplying by a constant value. And the growth factor b is going to be equal to 2. Now my value for a, I can't see on the table, but what we can do is go backwards. So what I'm going to do is add some values to the table. I'm going to look at 1 and 0, and so if I'm multiplying by 2 in kind of this downward direction, to move in reverse, I would be dividing by 2. And again, I could just focus on the denominator. So 4 divided by 2 is 2. So at 1, I would have 2/3. At 0, so 2 divided by 2 is 1, so 1/3. And then you could just double check, okay, times 2, it fits in with everything. So making my exponential function, we're going to have f of x equals, and now we have our initial value. So at 0 is 1/3. So our initial value is 1/3 times growth factor of 2, and then our variable, which will just have bx. Then if you're unsure if you set this up correctly, you can always check, like plug in, let's plug in 3. So if I plug in an exponent of 3, well, 2 to the 3rd power is 8 times a third, 8/3. So we're all good to go. All right, now down here it's going to get a little trickier. So what I can see is with x, it's not always the same amount. So to get from -1 to +1, we would add 2. And with x, we always look for addition, not multiplication. So we would add 2 there, add 1 there, add 4 there. So a lot of different changes happening here. What I want to kind of focus on is this scenario where we just change by 1. That really gets at either our slope or the growth factor that we're using. So that's something to think about. Now with these, we have the improper fractions, which is fantastic. If it helps you to also see the mixed fractions, you absolutely can. Like 3/2 is the same as 1.5. 5/2 is the same as 2.5. So if that helps, you can have them there. What I can see is, let's see, to get from 3 to 5, or even to get from 2.5 to 3, could think about multiplication, but let's just think about addition for a moment. And that to get from 2.5 to 3, or to get from 5.5 to 3, all we need to do is add a half. So let's make that our change for a moment. 1/2 added on. So then let's go and see what it would take to get from 3/2 to 5/2. Now this is where I need to think about this plus 1/2 happened across an increment of 1. What I'm going to have here is it happening twice. So what I would have here is, if this plus 1/2 is really this rate of change, I would have plus 1/2 plus 1/2. Because what I'm missing is this step in the middle where x equals 0, but we're just skipping over that momentarily. So if we add 1/2, or if we add 1, that works great. Moving from there to there is the idea of adding 1/2 twice. And is that in between there's a step where we'd only add a half once, which would take us to 2. So we can see adding 1/2, adding 1/2. Sorry, my dog is shaking in the background here. All right, and then adding 1/2 to get to 3. So then to really check that this works is that to move from 3 to 5, we would be adding 1/2 4 times, which is the same thing as adding 2. So 3 plus 2 is 5. So what this comes down to is addition. It's just when we have these different jumps that aren't just 1, we have to think of them in different increments. So this is linear because it's addition. And what I kind of snuck in here is our y-intercept would be at 0, 2. And then our rate of change, which is slope, is this positive 1/2. So our function is linear, where m is 1/2 times x plus 2. And again, we can plug in values to make sure it works. Like if we plug in x equals 2, 2 times a half is 1, 1 plus 2 is 3. And then we can plug in 6, and it would be a 3 plus 2 for a 5. All right, our last one here. So what I have is checking out x first. You can see we're adding 2 and adding 2, so we have these jumps of 2 and then this jump of 1. So I'm going to kind of focus on this jump right here. So to get from 5/9 to 5/27, what I can see is that the numerator didn't change at all, but the denominator did. So if we think in terms of multiplication, if I multiplied by something, it would have to be a fraction because only the denominator is changing. So the numerator would stay the same as 1 over. And then you could just focus on, what do I need to multiply 9 by to get to 27? Well, that needs multiplication by 3. So it's kind of like we're dividing by 3, or this multiplication by a third. So if we want to check this for our other values, again, since we're moving by 2 here and not 1, we need to do this action twice. So it's like we're multiplying by a third and multiplying by a third. Or you could think of that as multiplication by 1/9. So if we take 45 times 1/9, or it's like 45 divided by 9, that would give us 5, which is perfect. If we did it for the next step, times a third, then we would have 5 times 1/9, which would give us 5/9. So that works great. So just look for these steps of 1, and that can help kind of give you an idea of where to start, and then you can check it for the other increments of change. So this is exponential because we're dealing with multiplication. And from there I'll form my function. So our initial value, 0, 5. Oh, we're so close to the end here, and my dog is just making all the noise. So sorry if my dog is distracting. But let's finish up. So initial value of 5 times our growth rate is that 1/3. And then that 1/3 will have an exponent of x. Now if you're using the fraction form, be sure to use parentheses, because if you write this as just 1/3 x, it could be interpreted as just the numerator having the variable. So if you use the fraction, use parentheses as well.